So, welcome to the walkthrough of our mechanics mock exam. So, particle moves with constant acceleration 2I minus 3j. So, we have A equals 2I minus 3j. Step 1. At time t equals 0, P has velocity 4I. So, we know the initial velocity equals 4I. And it says find the velocity at time t equals 2. So at t equals 2, what is v? So we can use a formula from year 1 mechanics. V equals u plus at. Remember that Suvat equation. And then this question becomes easy 2 out of 2 marks. So we're going to get v equals 4i plus 2 times a, which is 2i minus 3j. And if we expand that all out, you'll see you'll get 4i plus 4i minus 6j. So v equals 8i minus 6j meters per second. Now the year 2 version, which you should know how to do also, is v equals the integral of a in respects to t. So dt. So in this question we have v equals the integral of 2i minus 3j dt. So v is going to equal 2ti minus 3tj, and remember the constant of integration, plus c. Now to find this constant, we can use our t equals 0, v equals 4i. Let's sub in these values in. So 4i is going to equal 0 here, minus 0, plus c. So c, 4i is going to equal c. So we have our velocity equation now is 2ti in respect to time minus 3tj plus 4i. Now let's select t equals 2. And we're going to get v equals 4i minus 6j plus 4i, and then we get the same answer as before, v equals 8i minus 6j meters per second. Hope that makes sense, and that's a nice 2 out of 2 marks. Now let's look at part B. At time t equals 0, the position vector of P relative to a fixed origin O is I plus j. Find the position vector of P relative to O at time t equals 3 seconds. So from that, we still have from before u equals 4i. The acceleration is still 2i minus 3j, but this time t equals 3 seconds. Now we're looking for the position vector, and so the Suvat equation we need to use is s equals ut plus a half at squared. So let's substitute the figures in. We have s equals 4i times 3 plus a half 2i minus 3j times 3 squared times 9. So let's work all that out. That's going to give us 12i plus 9i minus 27 over 2j, which gives us 21i minus 27 over 2j. Now that's going to get us a method mark. Now this would be the answer if it started at the origin. But on this question, you can see it starts at I plus j. So we need to add this on. So we need to add I plus j to our final answer, which will leave us with 22i minus That's 13.5j, so plus j minus 12.5j. Now that's something we could quite easily miss, but I hope that makes sense to you now. Okay, so this is worth 12 marks, so it's easily worth more than a grade, just getting this right. This is a small stone A of mass 3m is attached to one end of a string. So let's label that. What we can label here is we're going to get down here 3 mg. Now remember the normal reaction going perpendicular to this plane. That's R. Now you've got a string, so your tension is going this way, and this string, if this weight is pulling this down, you're going to have tension going up the string. A small stone of mass B of mass m is attached to the other end of the string, so we're going to write mg here. A is held at rest on a fixed rough plane, and it does say, if you read the whole question, stone A is released from rest and begins to move down the plane. Because it's rough, and when it's released, as A is travelling this way, then friction must also be working that way against the direction it's travelling. That's really important, and that's why that will confirm why the tension is going this way as well. So now we've got tan theta, we've got to use this bit, or tan alpha equals 3/4. So I suggest you draw the 3-4 triangle somewhere. That must mean that's 3, that's 4. That's opposite and adjacent. Now you know Pythagoras theorem, that's a 3-4-5 triangle. So you know tan alpha is 3/4. Sine alpha, opposite over hypotenuse, that's 3/5. Cos alpha is going to be adjacent over hypotenuse, so that's going to be 4/5. Now let's finish this diagram here. We know this is the right angle. We've got the 3 mg going this way. So going down this way, what would that be? In relation to this force, that's going to be, remember if this angle is here, that's the adjacent, so that's the cos. We need to use cos, so we're going to get, this is the hypotenuse here, so we're going to get 3 mg cos alpha, which we do know is 4/5, we'll use that later. And this way, if you can see it clearly, that's got to be 3 mg sine alpha. Now that is our diagram fully labelled, and that will help us start this question. Now part A says, using the model for the motion of a system for B reaches the pulley, write down an equation of the motion A. Now that just means B will reach the pulley because as A goes down this way, B will go upwards, okay? Now we have to model parallel to the plane, because like I said, A is going this way. Now what do we know? We know F equals ma. So resolving, I'm going to say parallel. We can see, what do we have going this way? We have 3 mg sine alpha what's going the other way is T and F, so that's the friction, so we have minus T minus F equals, now remember in this instance we are modelling this A here, m equals 3m. So we get that must equal 3ma, which is using our force equals ma diagram, right? Now part B says show that the acceleration of A is 1 over 10g. So that's the acceleration of A here going down here is 1 over 10g. Now this is going to be a little bit challenging, but we have to resolve in every direction. So let's start with part B here. So let's first resolve perpendicular to the plane. So this is what we're resolving here, this r. So that what we're going to get is r equals this here, 3mg cos alpha. We do have this figure here, and we'll substitute that in at the end. Now we have F max equals mu r, and we know mu equals 1 over 6 as it's given right here. So the friction F is going to equal 1 over 6 times 3mg cos alpha, which is going to equal a half mg cos alpha. We're going to call that equation 2. Now we've got to resolve upwards, and this is on B here. So that's going to give us the tension minus mg is going to equal ma, because F equals ma. So T equals ma plus mg. That's equation 3. Now remember from part A we have this, so we could substitute this in, and our values for T and F above. So we're going to, from using 3mg sine alpha minus T minus F equals 3ma. Let's substitute all those figures in. We're going to get 3mg sine alpha minus ma plus mg. When we take the bracket out, that's all going to become minus, and we're going to get minus this half mg here, cos alpha here, and that's going to equal 3ma. Now we can divide out by m, cancel m by dividing, which leaves us with 3mg. Now I'm going to use the sine values and cos values from here. So 3mg, no, so, oh, I've cancelled out m, so that's 3g times 3 over 5. So I cancelled out the m here, so minus a minus g minus a half g. So just going to show that m's cancelled out, that'll be easier. And cos alpha is 4 over 5 times 4 over 5 equals 3a. Now we're going to combine all the terms. So let's get 9 over 5g minus a minus g minus 2 over 5g, just simplify this term here, equals 3a. And then if once you rearrange a's on one side and the g's on one side, you're going to get 2 over 5g equals 4a. So divide that by 4, you're going to get 2 over 20g equals a, so a equals 1 over 10g. And that's finally done. Now that is quite complicated and easy to make mistakes. So that is a really challenging question. Do try it just so you've got the skills to earn some method marks for the future. But you've done it. Remember to go back to the beginning and try this question again on your own and see if you can get it right. So part C says sketch a velocity time graph of the motion B from the instant when A is released from rest to instant just before B reaches the pulley, explaining your answer. How we do this would be, that's V, that's T, and it says B just before it hits the pulley. Now think about it, if that's accelerating at 1 over 10g, let's write that like that. That acceleration is constant, every second it's accelerating the same. So acceleration is constant, and for part D, the string is not light, and so the tension on either side of pulley would be different. Okay, we have a beam AB with mass m and length 2a. Now, can you see it rests in equilibrium with A on rough horizontal ground? So we think, to help us do this question, if this beam was to slide off, it will go this way, it will slide this way, so friction must act this way, because there's going to be friction. The wall is smooth, so there's no friction here. It's inclined at a horizontal at an angle theta, shown in figure 2. The coefficient between the beam and the ground is mu. The beam is modelled as a uniform rod. So if it's a uniform rod with mass m, then we're going to get mg at a distance of a, half of 2a. Now there's some things we need to remember. There's going to be, going straight up, a reaction that we're going to call it A, a reaction this way, and we're going to call that B. And because we're going to have to take moments, and it's got to be perpendicular, we're going to have, that's going to be theta, so we know that's mg cos theta, and this way is going to be rb sine theta, and that's nicely labelled here. Now we need to show this here. So in all of these types of questions, we're always going to start off with, this is part A, f is less than or equal to mu r. Now we know mu is going to be greater than something, so it makes sense that if we look this way, mu is going to be greater than what we normally call f max. Now let's do what we normally do, resolve in all the directions that we can. So let's start with resolving directly upwards, so the y-axis as such. So we can see that RA, this is the only one going up, is going to equal mg. Now I'm just going to label that as 1. Now which other ways can we resolve? We can resolve horizontally. Should put that in a bracket. So what have we got horizontally? We've got f going this way. So f is going to equal, hopefully you can see this, RB. So I'm just going to go through this question very carefully, so hopefully you can really understand what's going on, because there is many steps, so I can totally understand that this is a complicated question. Now we have to say that f is less than mu RA. Now we sub in 2, so f is in fact RB, we get RB is less than mu of RA. So let's do a little a there, and then sub in 1 where RA is mg. We then get RB, little b is less than mu of mg. So this is so many steps here, and I can see why students will struggle with this question. Year 2 mechanics is very challenging. Now let's take our moments. So I'm going to do this over here. Moments from A, and that is big A. So our anti-clockwise, can you see, is AMG cos theta. So it'll be AMG cos theta, which is going to equal the anti-clockwise, right? Which is going to be 2A times, now we know RB equals mg, but we're going to call it RB sine theta. Now anti-clockwise and clockwise are equal, so we're going to get A times mg cos theta equals 2A minus 1 sine theta. Now we're going to remember later that RB, reaction at B equals this, not mg. And we can cancel out A's to get mg cos theta equals 2 RB sine theta. Now we know cos theta over sine theta is actually cot theta, and sine theta, let's write this down, sine theta over cos theta equals tan theta. So we are going to get this 1 over tan theta here. So once we isolate the reaction B, we're going to get mg cos theta divided out by sine theta here, 2 sine theta. We're going to get something that looks like this bottom bit here, which is looking really nice. So this is an important equation, and I'm going to call that equation 4, and this is a key equation that we reference, that's equation 3. So sub this into, sub 4 into 3, so subbing this into here, so we get mg cos theta over 2 sine theta equals that reaction at B, which is, can we see, mu mg. Now we can divide out and cancel out the mg's. Now I should keep the inequality sign in. So we get cos theta over 2 sine theta. So then mu, which is in fact, this is in fact a half cot theta, or as the question appears in your paper, if it makes sense, if this bit is tan theta, then the inverse cos theta over sine theta is going to be 1 over tan theta. So mu is greater than 1 over 2 tan theta, and it's just written the other way here, and you can just clean it up a bit. Mu greater or equal to than 1 over 2 tan theta, which is also, which you'll need to know later on, is the same as a half cot theta. Now that took a long time to explain, but there's lots of steps. Do try that question again because there's so much to it. Now it says we've got part B here. Now it's changed because a horizontal force of magnitude kmg, where k is a constant, is now applied to the beam at A. A horizontal force of magnitude kmg is applied at A, so it must be here. We've got a kmg acting this way. So if this is acting that way, we're going to get friction changing direction. So friction is not going to act this way anymore, it's going to act that way. That's important. We're still going to get mg because it's uniform. Now we've still got this RB here. We've still got RA, the reaction force at A. Right. Given that tan theta equals 5 over 4, so this is the hypotenuse, opposite and adjacent. All that means is this is 5, that's 4. And we can use those exact figures later on. So let's do what we normally do. Which way can we resolve? Let's resolve horizontally first. And what do we get? We get, can you see, we get this kmg here. So we've got kmg. It's got to equal F that we have going this way and RB. So the reaction at B. Now we know F max is going to equal mu of Ra. and mu is a half, so we have F max equals a half R8. Call that equation 2. So let's sub 1 into 2, or 2 into 1. So our half RA is here. So what we get here is KMG equals a half RA plus RB. That would have a nice equation here. Now if you resolve vertically first, that's fine as well. You'll eventually see what you need to do, but let's resolve vertically. What's going up? We have RA. It's going to equal what's going down, so that's equals mg. So we know RA equals mg, we can substitute it into here. So now we're going to get KMG equals a half mg plus RB. Now what haven't we done is we haven't taken our moments, and we're going to use our moments to get a term in front in terms of RB, so that we can find the value of K here. So let's do our moments up here for space. So moments from A, you could do it from B as well, but you get a slightly different answer working out, but the same answer. Now that's the same as in part 3A, isn't it? So we're going to get A times mg cos theta is going to equal 2A, the distance, because that's the distance 2A here, RB, reaction at B sine theta. Now we can cancel out A's here, so we get left with mg cos theta equals 2RB sine theta, reaction at B. Now we're going to get our terms in terms of RB, so we're going to divide out by 2 sine theta on both sides. Theta on both sides. So we get left with mg cos theta over 2 sine theta equals the reaction at B. So we're going to label that 4. No, let's label that, not let's label that 4. Let's label this 4 and sub this into 4. So you can see what we'll get here is KMG equals a half mg plus mg cos theta over 2 sine theta. We can cancel out mg here, mg's in every term. So what we're going to get is K equals a half plus, once we cancel out the mg, that is, we're going to get 1 over 2 tan theta, I mean. So 1 over 2 tan theta. Now we know tan theta is 5 over 4. So if we do 2 times 5 over 4 equals, so that actually equals a half plus 1 over 2 5 over 4. That actually is going to give us 9 over 10. I wouldn't say that is quite easily done, there's so many steps to this, but hopefully if you can pick up a lot of these skills, you can, it's going to boost you up an entire grade, isn't it? This is. So do watch this more than once, and I hope that helps. And there are of course the work solutions that was wonderfully provided by another member of the department that you would have access to as well. I've just done this because it might be easier for you to understand walking through it step by step. I hope that's helpful.